Hello everybody. I am going to tell you about the worlds beyond our own world, that is our solar system. So, these are planets which are outside the solar system, the planets that are orbiting the other stars very similar to our own star, the sun. Now, the question is, why do we need to study for other worlds? Why we need to know about extrasolar planets or simply which are called as exoplanet? Because a scientific study of this subject leads to a possible answer of the eternal questions or the eternal query of mankind, that is there anybody out there or are we alone? Now, study of these extrasolar planets or the planets outside the solar system, it enable us to understand on the planet formation mechanism, whether we know very well how the solar system has been created some 4.5 billion years ago, but we do not know whether that is a general case. So, this is a nice area to understand whether our present knowledge on the formation of planet, that is the solar planet, is a particular case or it is a general case. Is the solar system unique or is it common in our galaxy? Our solar system has a very specific configuration, that is all the small rocky planets are very near to the star, that is the sun, and all the gaseous giant planets are outside. They are called the gas planet or gas giants. So, the question is that is all the extrasolar planet or planetary systems are similar to the solar system, that is there also the giant planets are outside outer planets and the rocky planets are the inside planets. Then the next come are there planets similar to the earth? The planet earth, you know, it has a very special characteristic. It has a rocky surface, it has a thick atmosphere, it has a very massive natural satellite or moon, it has a magnetic field, it has several geological special characteristic. So, is there anywhere a similar planet like earth? There is no similar planet like earth in our solar system, but what about the planetary system outside the solar system around the other stars? Can we find out another earth? Because that will answer the question whether life is possible in another planet or not. So, naturally then another related question or more fundamental question arrive, what is the origin of life in our planet? Has life originated in the planet itself or it has been imported from outside? Is it very common in our galaxy or in our universe, or is it a special case for just one planet, that is our earth? Now, there are a large number in our own galaxy, there are 200 billion of stars. So, this has given the imagination of human being that there could be intelligent life everywhere, there could be life everywhere in the galaxy. But if that is the case, then where are they? Why do not we get any signature? Why do not we get any activities observed in the solar neighborhood that tells that everywhere there are planet intelligent life or even primitive life? So, that is a question asked by Enrico Fermi, the famous physicist, where is everybody? So, what is the problem? Now, we know one planet very well, that is Earth, and for thousands of years we know that this Earth or our world, that is not enough, and we are a member of a family of planet that is called the solar system planet. So, for more than 80 years we knew that there are 9 planets, but in 2006 at International Astronomical Union, the definition of solar system was re-examined, and it was decided that Pluto is not a planet, it is not very similar to the other planets in the solar system. So, it is now considered as a dwarf planet. So, in the solar system we have only 8 planets, but this definition, the change of the status of Pluto was driven by a large number of exoplanet outside the solar system. The first planet that has been discovered by Professor Michel Mayor of Geneva Observatory, and this is around a star, is a very similar to our sun, is called Pegasi 51, and the planet is designated at Pegasi 51b. So, here is the location of the planet. You can't see the planet here. Now, once this planet was the first planet was confirmed around this solar type of system. So, there was a search, huge search initiated to find out other planets, and everybody, all astronomers using all type of telescope throughout the world started hunting of planets, and 100 of planets has been discovered each week, each month, each year the number of exoplanets started increasing. So, this search was done mainly by the ground based telescope that ranges from 1 meter diameter to even 6 meter to 10 meter diameter telescope. But because of the signal or because of the limitation in the ground based technology, the search was limited only within 300 light years from the sun, that is within the area of 300 light year in the sun. But then in 2009, a space telescope named after Johann Kepler was launched, and that is called Kepler telescope. So, NASA launched this Kepler telescope, and after this Kepler telescope was launched, the European Space Organization also launched another space telescope called COROT with the same purpose, that is to detect planets outside the solar system. Now, this space telescope that has extended the search area by 10 times, and with Kepler we can search for exoplanet up to 3000 light years, but in a narrow region of our galaxy. Now, once Kepler before the Kepler was launched or before the exoplanet was detected, we knew about the solar planets, we knew about the temperature, we know that Venus is the hottest planet in the solar system, although Mercury was the nearest planet, but since Mercury didn't have any doesn't have any atmosphere, and because of the presence of a thick atmosphere, Venus is the hottest planet, which is of very similar size to Earth, whereas Mercury is a subterrestrial size, it is much smaller than the planet Earth. Similarly, Earth has a temperature which is very appropriate for the water to stay in the liquid form. Then Jupiter is a giant planet, several times larger than our planet Earth, is a gas planet, and then Saturn, Neptune, and Uranus and Neptune, and the coolest planet in our solar system is Uranus, although Neptune is the farthest, but this is all because of the atmospheric effect. Now, once Kepler was launched and we found several kind of planets, it was the properties of these planets, the temperature, the size, all went beyond our imagination. Now, we find planet which are much larger than almost double of Jupiter, whose temperature is much higher, even 2500 degree to 3000 degree Celsius, where iron even melts, and we get different size of planets. The planets which are in the transition state of gas planets and rocky planets, which are smaller than Neptune, but bigger than Earth. So, all kind of planet we have discovered, which was beyond our imagination even few years before. Now, if you consider the size, the Kepler has given such type of size that we define the Jovian planet or the Jupiter size of planet, whose radius ranges from 6 to 20 times that of the Earth radius. Then come the Neptunian, which ranges from 2 to 6 Earth radius. Then come a particular size of a planet which does not exist in our solar system, and these are called mini Neptunes. So, probably these planets, they have a rocky core, but it has an extended atmosphere. So, these are in the transition of a rocky planet and a gaseous planet. Such type of planet or the mini Neptunian does not exist in our solar system. Then there are super Earth, which are larger than the Earth in size, but they are very similar to Earth. So, their radius ranges from 1.25 to almost double of the Earth radius, and their mass is only few times that of Earth mass. These are rocky planets, and these are called super Earth. And then comes the Earth, and then come the sub Earth, sub terrestrial like our Mercury. So, you get a various range of planets by temperature, means how hot they are, and by their size. Now, if you classify all the solar planets by size and by the temperature, you can get only 7 type of objects in our solar system, including the natural satellites, that those are the moons of the various planets. You know, the largest moon in the solar system is Ganymede, which is a natural satellite of Jupiter. Our moon is the 5th in its size. Now, the other planets are there. The only planet in the temperature range where water exists in liquid state is only Earth and sometime Mars. But when we discovered all these planets by Kepler, by Corot, by the several ground based planets, we found out 17 kind of planets in our galaxy itself. That ranges from Mercury size to several times Jupiter size and Jupiter mass. So, this has changed our entire concept on the planet, on the planetary properties, on the planet formation, because now we do not see any planet that has the small or the rocky planet near the stars and the gaseous planet outside. We have seen many of the giant gaseous planets are very near to the stars, and rocky planets are yet to be discovered in that type of system because of the limitation of the technology. But the presence of a giant planet very near to the stars clearly tell that the solar system is not unique. So, we have a diversity not only in the planets, but in the planetary system itself. Now, how these planets are detected? The main problem for detecting planet is the brightness of their star. The planets are hidden under the intense temperature of their stars. So, astronomers take indirect method to get the signature of this planet. And now, I will tell you the major detection method, how these planets are, how most of these planets are detected. There are quite a few methods which are popular among the astronomer. At the initial stage of the detection of exoplanet, and by the method through which the first exoplanet 51 Pegasi b around the solar type of star Pegasi 51 was discovered by Professor Michel Mayor, is known as the radial velocity method or the Doppler method. Now, we know that when a binary system in a binary system, when a object rotates around another object, none of them rotate exactly around the center of another object. They rotate around their center of mass. Now, the center of mass, the position of the center of mass depends on the mass of the two binary components. If their mass are same, then the center of mass is just in the middle of their distance. Now, in the case of a planet orbiting a star, the planet does not orbit exactly around the center of the star, but its center of mass lies outside the outside the center of the star, not necessarily outside the star. As a result, the planet's gravitational force that gives rise to a radial velocity to the star, and that is just like a wobbling of the star. Now, when a star moves towards you, the light get blue shifted, and when it moves away from you, the light get red shifted. This is known as Doppler effect. Now, because of the planet, the stars wobble and the stars moves towards you and then moves away from you, and that gives rise to a Doppler shift. So, you can see that what is happening there, that the light of the star then pass through a spectrograph, and then the various lines which are caused due to the absorption in the atmosphere of the star are monitored. They usually pick a iodine cell or a argon cell, and then see that how that line moves towards the blue region or towards the red region of the spectrum. So, here you can see that when a planet moves around the stars, the star also moves towards you sometime and towards away from you sometime, depending on the position of the planet. And when it does so, the lines, the absorption line in the stellar spectrum, that moves periodically towards the blue region and towards the red region. So, this property is exploited by the astronomer to detect the signature of the planet. This method confirms the presence of a planet. It also tells about the period, the orbital period of the planet, because once movement towards the blue and then returning to the center gives one period, and it tells about the projected mass of the planet, because that projected mass is the function of the orbital inclination angle. This method cannot tell you about the inclination angle of the planetary orbit, and hence it cannot give you the exact mass of the planet, but it can give the projected mass of the planet. And also it cannot tell about the size of the planet, because the entire method depends on the gravitational effect on the mass of the planet, and if we know the mass of the star as well. The next method, which is called as transit method, it has become very popular, and the Kepler telescope or the Corot telescope, other space bound telescope, they exploited this method, is known transit method. Now, what is this method? You have already witnessed a solar system phenomena, that is the transit of Venus across sun. So, what happens there? The shadow, when the Venus passes across the sun, the shadow of Venus falls over the disk of the sun. As a result, although Venus is very tiny, it causes a decrease in the total brightness or the flux in the star. So, this phenomena is exploited for the other solar system, that is when a planet is very near to the stars and it has a very high inclination angle, it is rotating like this way perpendicular, not like this. Then a part of the stellar disk is blocked by the planet, the shadow of the planet, and the astronomer measure this drop or the decrease in the stellar light, and from that they can find out, they can confirm the presence of a planet, they can confirm the period of the orbital period. Not only that, unlike the case for radial velocity, here they can find out the orbital inclination angle as well as the radius of the planet. So, when a planet is discovered by transit method, it can give the radius of the planet and the inclination of the inclination angle of the orbit, and then they repeat this planet by radial velocity method, which gives rise to the mass. since now you have the orbital inclination angle, you can, by combining the result of radial velocity and the transit method, you can find out the exact mass of the planet. And since you know the radius of the planet from the transit method, you can determine the mean density of the planet, and from that mean density of the planet, you can determine whether the planet is gaseous planet like Jupiter or is a rocky planet like Earth or Mars or Venus. The another method is known as gravitational microlensing. So, this method is based on Einstein general theory of relativity. So, according to Einstein general relativity, we know that the curvature, the space time curvature around a star is curved, and the light even also bends when it passes through a near a star. So, what happened here, that when a distant star, the light of a distant star passes through a lens star and then comes to us, the light bends towards the lens star, and that gives rise to a lensing effect. It is just like your ordinary glass lens type of thing. Here the intensity, the light of the star magnifies because of this gravitational field of the lens stars. So, now what happened here, when a star moves towards when the light of a distant star moves towards a lens star, then the brightness start increasing, and that is called gravitational microlensing. And then after that, as it passes by the lens stars, then the intensity, the brightness of the stars, it falls down. This is known as gravitational microlensing. Now, this is happening for the light of a distant star that is passing very near to a lens stars and coming to the earth. Now, if the star, the lens star has a planet, then as it falls the light, as the system with the planet goes away and the brightness of the star falls, because of the planet it again picks up, because the planet also gives rise to the gravitational microlensing effect, and then again it starts falling down. So, by monitoring the entire light curve, that is the brightness, increase in the brightness of the background star, that is distant star, and then falling over it, in between there is a sudden rise in the brightness of the distant star caused by this lensing star, the astronomer can tell that there is a planet. But this is a very chance effect. It can, although it has an advantage that it can detect a planet far away from its stars, it cannot give the exact mass of the star. What it can give is the ratio of the lens stars and the planet, and it cannot give the orbital period or any other thing, and this method, the detection method, cannot be repeated again because this is a chance effect. So, gravitational microlensing, through the gravitational microlensing, quite a few good number of planet has been discovered, which are very small, which were not possible to be detected through radial velocity method or the transit method. Nevertheless, this remains as a potential method to detect small like Earth like of planet. Now, besides these three method, there are quite a few other method like astrometry method. Now, incidentally, I should point it out here that the search for exoplanet has started as early as in the 19th century, and at that time astronomer used to follow the astrometry method in the mostly in the binary system, and the first false alarm for a planet has been reported by Captain William Jacob of Madras Observatory. At that time it was under the East India Company. Later on it was taken by the British government, and that observatory traces back the Indian Institute of Astrophysics, which is now at Bangalore. Now, Captain William found that a pair of star, a binary star system, that is Ophiuchi, that is called Ophiuchi. So, they are not following Kepler's law exactly. There is some deviation in the orbital motion of this the star system Ophiuchi. So, he predicted that a planetary mass object may account for this anomaly in the orbital motion of this star. But later on when instrument or the technology improved, it was found that this was a false alarm. There was some error in the data, but then further recently when this was follow up, it was found that there is a possibility that there may be a planet in this system, we do not know, but there is a lower limit on the mass put on that star. So, officially this observation or the Ophiuchi is considered as the first false alarm for exoplanet. But then subsequently several astronomers attempted and reported, but all of the result was found to be false alarm until 1995 when Michel Mayor of Geneva Observatory confirmed the first planet around a solar type of star. So, that is a different story. Now, this method, these three methods or the astrometry method, this can detect planets which are nearby, relatively very near to the stars, and their light comes by the reflection of their starlight, they are very nearby. So, they cannot be imaged directly or they cannot be seen directly unless and until you can block the starlight, but the planets are also no planet has their own light, they are only emitting their reflected light. So, they are very faint. So, even if you block these stars, you may not get an image of these planets with the existing telescope. But there are some planets which are very young. The planetary system itself is 10 million year to 100 million year old. So, the planets are still forming, they are still very hot and their temperature, their own temperature is about 800 degree Kelvin to even 1400 degree Kelvin. And so, they are bright especially in the infrared light. Now, these type of planets are far away from their stars. Many of them are about the distance from Sun to Pluto or even more 30 astronomical unit to 40 astronomical unit. So, the astronomer could block the starlight and then take the image of these planets, and in this way astronomers have taken the image, the real image of quite a few planets by direct imaging, and these planets are known as self luminous planet or directly imaged planet. This is the first planet in the red one that is imaged by this direct method by blocking the star, and here you see this star, this is called 2 mass 1207. This is actually not a star, this system is a very interesting star. So, after the discovery of these several planets and the mass, there was a question that so what is the maximum mass of a planet, how you will define the planet, because we know that the stars are formed out of the collapse of interstellar cloud, but planets are formed out of the protoplanetary disk by the coagulation of the dust and the gas that was remained after the star was formed. But you can't see 4 billion years ago what happened, how a planet was formed. So, how will you define that what will be the maximum mass of a planet? So, there is no way to know it. The astronomer thinks that the planet which does not, the mass of the planet which does not exist about 13 Jupiter mass, they cannot ignite nuclear burning in their center, that we call deuterium burning, that is the initial stage of nuclear burning inside star. So, they define that if the planet, if the object is lighter than 13 Jupiter mass, it can be considered as a planet. Now, the thing is that this nuclear burning has several stages. So, if the object is heavier than 13 Jupiter mass, it could ignite deuterium, but it failed to ignite helium, and therefore, it cannot sustain the nuclear burning and it cannot become a full phase star. A continuous supply of energy is not possible in such type of star. A star needs further reaction which is called the helium burning, and that is possible if the center core of the object exceeds 10 million temperature, and that is possible only if the mass of this object is more than about 80 Jupiter mass. So, the question was there, what will be happen between this, that is between 80 Jupiter mass and 13 Jupiter mass, and those type of objects are known as brown dwarf. They were the missing link between the stars and the planets, and incidentally the first brown dwarf was also discovered in the year 1995. So, these are the Mie star. So, here in this system 2 mass 1207b, you see the star, this object in the center, the primary component has failed to become a star, whereas the second component whose mass is 10 Jupiter mass, which has failed to become a brown dwarf. So, this is a very interesting object, and this is the first direct image of a planet. Subsequently, astronomers have used a large telescope and imaged many other planet and planetary system. One very popular planetary system is this one HR 8799, where not only one planet, there are 3 planets has been discovered B, C, D, and later on one more planet was discovered, that is E. So, this system you see can in between the star light is blocked by an instrument called coronagraph, and the planets are so hot that their thermal radiation can be imaged by the photometer on board the earth. These are all ground based telescope which has taken the image. Subsequently, there are many other planets which has been imaged. Here you can see Beta Pictoris b, where the planet is just born. So, the protoplanetary disk can also be visible in this picture, and with time we could see that the planet is moving very slowly, but because these planets are far away from their stars. So, we cannot make out exactly what is their period, we can make the dynamical mass of this object. So, next come see another planet which is HD 95086 b, the star name is HD 95086 and the planet is designated by that number b, and then come one more. So, the number increases and it makes a awesome album of exoplanet. Now, these are planets, planetary system around star. There are planets which are discovered as a rogue planet or free floating planet. So, they do not have any parents like our sun or any star, they are just free floating. We really do not know how they are formed. They are formed just like brown dwarf, means due to the collapse of a cloud, or they are a detached planet from a planetary system, we do not know how they are formed. So, this planet does not have a parent. At the same time, we have discovered planets that has 2-3 planets, that they are called circumbinary planets. You know, our nearest stellar system other than sun is called Alpha Centauri. This is a system of 3 stars, Alpha Centauri A, Alpha Centauri B, and there is a third component which is a very faint star, that is called Proxima Centauri. Now, around Proxima Centauri a Earth size planet has been discovered, and that is the nearest exoplanet to us. So, this planet has 3 parents, it has get light from 3 stars, its climate is governed by the temperature or by the heat energy by 3 stars. At the same time, astronomer has detected planet which could be made of diamond instead of rock, because the solar system when it was formed, the primordial cloud that formed, it has equal amount of oxygen and carbon. Now, some of the system which was formed out of some interstellar cloud that has more carbon, then the star is called carbon rich star or carbon star. Now, a planet around the star, if it is rocky, then it because of the tremendous pressure inside its crust and temperature inside its core, this carbon can form in a crystal, and that is a diamond. So, the entire crust or surface of the planet could be diamond. So, there are various kind of planet that we have discovered which are beyond the imagination of astronomers, and the diversity of the planets is worth studying, but our final aim is to find out a planet very similar to Earth where life can be possible. Now, you know, in our galaxy there are 200 billion of stars. So, it is not possible by even a supercomputer or whatever be the telescope we have to search for each and every planet. So, the astronomer takes some strategies. So, they find out the places in our galaxy where it is favorable to have a planet, and that is also it should be rocky planet where life could be possible. So, this is called this type of planet we will call the habitable planet, and I will come to define very soon that what is this habitable planet. So, the position of the stars in the galaxy which are favorable for planet formation and hence the life formation is called the galactic habitable zone. Now, here you can see that this is our Milky Way galaxy, which is a spiral galaxy. Now, we need a region where the metallicity are very high, that means where the higher elements, the heavier elements exist, because if the star or the planet is made of only hydrogen and helium, then it cannot be a rocky planet. So, there cannot be carbon based life. So, the region that we need to find out where the metallicity is higher. Now, this is possible only in the outer arms of the Milky Way galaxy. As you go outside, the metallicity drops. The metallicity higher in the center, but the center is a very active region. Here the radiation is very strong, because it is supposed it is believed that there is a massive black hole sitting in the center, and that is causing a very violent environment in the center region. So, we omit that region, and then we find out that only along the arm in this direction the metallicity should be quite high, but not in the outer region where the metallicity decreases. Now, we need to go for normal star which is not very bright, because the brightness, the age of the star depends on the brightness. The brighter is the star, the shorter is its lifespan, but to form the planet it may not take much time, it may take a few million or few 100 million years, but for the origin of life and for the evolution of life you need to give sufficient time, and if it is shorter, if the lifetime of a star is only few 100 million years, you cannot find out any life, or you cannot observe even a planet, because the planet will be also destroyed. So, we need to find out something, some stars which are not very bright, which are not very hot stars, which has at least 4 billion years of lifetime, 4 to 10 billions of lifetime. And then you need to determine some quiet region without any violent activities. So, the center of the galaxy is already ruled out, and the arm of this middle of the arm are very active region. They are the new star forming all the time, and there are supernovas and many activities are going on. So, the best place for life to survive is the gap between the arm of the galaxy, and you can see our sun lies in a gap of a arm, that is called the Orion arm between that. So, these are the region that will be searched to find out the planet which could have possibly life. Now, this is the galactic habitable zone. Now, a planet, we know that for life to be formed and to evolve, water, liquid water is essential. So, the region around a star where the temperature is appropriate for liquid water to exist is called the habitable zone of the planet of the star, or the circumstellar habitable zone of the star. So, remember that this is a criteria that makes the temperature appropriate for liquid water to exist. Now, quite naturally that depends on the brightness of the star and of course, the distance of the planet from the stars. So, depending on the brightness of the star, the distance of the planet, a region can be defined where the temperature lies between 0 degree centigrade to 100 degree Celsius, which is appropriate for water to exist in liquid form. Now, if somebody search for planet in the solar system from outside, say imagine that some extraterrestrial intelligent is searching for life also, and they find out the solar system, and they will find out that these 3 planets Mars, Venus and Earth are in the habitable zone if they consider only the brightness of sun and the distance of Earth, Mars and Venus. But every planet has certain amount of reflectivity. The starlight that it receives, certain portion of the light reflects away, and that is called albedo. For Earth, the 30% of the light gets reflected to the outer space. For Mars, it is 20% that is get reflected. For Venus, it is a whopping 70% the light gets reflected away. And if you consider this is this albedo, then the planet becomes all the 3 planets become very cold and none of them become habitable. So, what is the problem? What they are missing it? So, that is the atmospheric effect. Now, when the starlight enters into the atmosphere, it goes and hits up the surface, the rocky surface of the planets, and the radiation, the energy reduces, the wavelength becomes shorter and it emits in infrared region, but this infrared light, it gets scattered by the molecules of the atmosphere, and it gets multiple scattered and it cannot escape from the atmosphere. So, this infrared temperature is trapped in the atmosphere of these planets which has atmosphere, and it hits up the planet, the environment, the planetary atmosphere, or the ambient temperature goes up, and this is called the greenhouse effect. So, once you call the you consider the greenhouse effect, then you can find out that only the earth has that temperature which is which can enable water to exist in liquid form. Mars is already far away from sun, and Mars has a very thin atmosphere. So, it cannot produce sufficient amount of greenhouse effect. On the other hand, Venus has a very thick atmosphere and it has a runaway greenhouse effect, and its temperature is very high, and that is why although Venus is not the nearest planet to the sun, it is the hottest planet in the solar system. So, now depending on the brightness of the star, the habitable zone can be at different position of the planet. You can see that if it is a hotter star, the habitable zone will be far away from the star. If it is sun-like stars, it will be exactly where our earth is there, that is within 1 astronomical unit. And if it is a cooler star like M dwarf or even brown dwarf, then the habitable zone will be very near to the star, where the temperature will be appropriate for water to be in liquid state. But this is only one condition, that is the temperature, the ambient temperature of the environment should be sufficient for the water to exist in liquid form, but the planet has to be also rocky, otherwise it cannot retain the water in its surface. If the planets is gaseous planets in the habitable zone, suppose if Jupiter type of planet comes the position where earth is there, it may have water, liquid water even, but it cannot retain the water in its surface, because there is no solid surface in this type of planet. So, we have 2 criteria, one is the temperature, the ambient temperature of the planet, and the planet should be rocky. Now, where are these habitable planets? So, about 80% of the stars in our galaxy are M dwarf and brown dwarfs. The number of solar type of planets are comparatively much less than M dwarf stars and brown dwarf stars. And then The occurrence rate of planets with size between 0.5 to 2 Jupiter mass, that is subterrane and superterrane, that is sub earth to super earth range, which could be rocky, is almost half, that is 0.51% for around M dwarf star, which is given by the transit method. This is by the statistical process we can find out there that one planet per 2 M dwarf stars will have a rocky surface, and radial velocity tells slightly less this, that is 0.41 per M dwarf stars are rocky. Now, not all rocky planets could be habitable planet, because those rocky planets need to be in the habitable zone of the planet. So, the planet has to be rocky as well as it has to be in the habitable zone of the star. There is another question comes, are the rocky planets in the habitable zone of M dwarf really habitable? Because M dwarfs are cool stars. So, their habitable zones are very near to the stars. Now, these stars are very active stars, they emit copious amount of ultraviolet radiation, even strong X-ray. So, this can affect the planet because the habitable zone is very near, and a flare, occasional even though a small flare, can destroy the entire atmosphere of such type of planet, and the ultraviolet radiation or the extreme ultraviolet radiation can stripe out the molecules in the atmosphere, and it can make the planet parch or lack of water. So, the rocky planets in the habitable zone of M dwarfs are very unlikely to be habitable if you consider the activities of the star, the stellar activities of the stars. But still there are quite a few rocky planet in the habitable zone has been found out by Kepler, by Corot and by other planets, and the number increases, and these are our future targets, because right now from their mean density we know that they are rocky, we know that their temperature should be appropriate for water to exist in liquid, but we do not know that whether there is a atmosphere or not, which is very essential for life to origin and to survive. Very recently a colony of rocky planets in the habitable zone has been discovered, and many of you have heard about this object, is called TRAPPIST-1. This is discovered by TRAPPIST telescope, and later on several planets, many of them are habitable, has been discovered by using large telescope. So, the first planet that is discovered around this star TRAPPIST-1, the Indian Himalayan Chandra telescope has also been used. So, this planet has this star has 7 planets in its system. Out of that 7 planets, 3 are in the habitable zone. There are several, almost all of them are all the 7 planets are rocky planets, 3 of them are in the habitable zone, but they are very near to their star, and this TRAPPIST-1 star found to be very active, and therefore, it is very doubtful whether any of these habitable planet has an atmosphere or not. So, further study for the atmosphere of this planet or the signature of liquid water or even gaseous water in gaseous form need to be detected before we can tell that any of these planets are really favorable, really has a condition favorable for life to form and survive. Now, this is a observed data, that is this planetary system has been detected through transit method that I have discussed earlier. So, this data is obtained by using Himalayan Chandra telescope, which has served as one of the discovery data for this entire observation, and in India also there are quite a few telescopes that we have been using through this transit method to detect and to characterize various planets that are already discovered or yet to be discovered. So, it is very important thing, once you detect rocky planet in the habitable zone like TRAPPIST-1 system, the next step is to find out if there is a atmosphere in these planets, and then you have to probe the atmosphere, that what is the molecular composition of this atmosphere. Does it have the molecules that is essential for the formation of life? So, as I have told that it is important to probe the atmosphere of the planet now. So, to find out really a rocky planet in the habitable zone is habitable or not. Now, this needs a very sophisticated technique or technology. We need larger telescope, we need larger space bound telescope, because not only that we need to get a good spectra of the planet, we need a high resolution spectra of the planet, etc. But the astronomers has already chalked out the strategy for that, how to determine if there is a atmosphere in the planet and what are the molecule presence in that atmosphere. So, this probing the atmosphere of exoplanet, it is just at the initial stage of our research. What is the strategy or what we usually do it there? During the transit of the planet across the star, we take a spectrum, and then we take again a spectrum of the star when it is not in the transit. So, then we subtract this spectrum to find out the additional feature that will certainly come from the planetary atmosphere. Now, this is a tricky thing, because the ratio of the light from the planet and the star ranges from as long as 1 million to even 1 billion part of the star light. So, what we do that, we just observe the stellar light there, that is blocked by the planet, and some part of it is transmitted through the atmosphere, if there is an atmosphere, and this is called the transmission depth of the starlight. So, the transmission depth is defined as 1 minus f incoming, the flux incoming, and by the flux outgoing. Now, this flux incoming is the flux that is block, that is the stellar flux that is block, plus the stellar flux that is leaked through the atmosphere of the planet. So, we need to find out this transmission depth of stars having planet. Now, this has been done for a few planets, and we have got some data which are very recent work. So, here you can see the 3 yellow points are the water signature from a planet called HD 189733b. This is taken by Spitzer Space Telescope, and the spectrum, the transmission depth has been modeled, which is the blue line, and the 3 data point, the observational data point, that clearly says that this stars has water molecules, but it is a very hot star. So, the water is not in the liquid states, it is a gas giant, very hot gas giant. So, water is in the gaseous state. So, similarly, photometric data in different wavelength is taken from a object that is called HAT P11b, and that was fitted by model, and more than one molecule, water molecule and other molecule has been found in the atmosphere of this type of star. These are gas giant star. So, we know that they certainly have atmosphere, and this data says that they have molecules also. So, in future, when the 6 meter class James Webb Space Telescope will be operational, when the 30 meter class telescope, when the large Magellanic telescope, when the European extra large telescope will be operational within a 10 years period, we will be able to detect the molecules presence in the planets, in the habitable planets as well, and from that we can probe that what is the environment, what is the albedo of the planet, what could be the greenhouse effect, and hence what is the ambient temperature of the planet, whether the planet is suitable for liquid water to water to exist in liquid form, etc., etc. So, the search continues. So, what should be the strategy of the search that I have already described? Find out as many rocky planets as possible around all kind of stars. That can be done with the existing telescope, and that has been continued by ground based telescope and phase based telescope, and will be continued by the future large telescopes. Then target the rocky planets within the habitable zone of the stars. So, find out as many rocky planets as possible in the habitable zone of the stars, and then characterize the planets and the planetary atmosphere to know the ambient temperature of these habitable planets. And finally, there is a possibility that some of the giant planet in the habitable zone, they are not rocky. So, they cannot retain water in their surface, but a rocky moon around them could be habitable. But so far we have not yet detected a single moon around any exoplanet, although there are various attempts, there are various proposal or strategy has been proposed to detect such type of exomoon, and we do hope that within a couple of years we will detect the first moon outside the solar system, but nevertheless the possibility that a rocky moon of a giant gaseous planet in the habitable zone of a star could be habitable. We do not know that, but the possibility exists. And then finally, when we find out all the atmosphere of a rocky planet in the habitable zone, we will look for the biosignature in the planetary spectra that will confirm us the presence of life outside the solar system. Now, what are these biosignature? So, here is a spectrum of 3 planets that extraterrestrial intelligence could have thought habitable planet from outside, that is Mars, Earth and Venus. Now, you can see there is the ozone line in Earth that is missing from the other planets. Now, how this ozone layer, which is protecting us from the energetic ultraviolet radiation, is formed? This ozone signature is actually a biosignature. In the initial stage of the Earth, there was no free oxygen molecules. Oxygen was combined with all other atoms to form oxides. Now, after almost 3.8 billion years of its means 3.8 billion years before now. So, after say 500 million years or about 1 billion years, there is a bacteria called cyanobacteria that appeared in the earth, and it started doing the photosynthesis, and it took the carbon dioxide and emitted copious amount of oxygen molecules. And because of the cyanobacteria, suddenly the entire environment, the earth atmosphere composition got changed, and earth atmosphere become oxygen rich. In addition to this photosynthesis by cyanobacteria, there was volcanic activities and plate tectonic, which has also gave rise to a good amount of oxygen molecules, and the entire environment got changed. Now, this oxygen molecule, when it goes in the upper atmosphere, it get dissociated into oxygen atoms by the incident of strong ultraviolet rays. So, these oxygen molecules then combine with the oxygen atom to give rise to ozone molecules. So, therefore, the signature of ozone is a biosignature, and even the free oxygen molecule, the signature of oxygen molecule is also a biosignature. So, once the habitable planet is detected, once the atmosphere and the spectrum is available for a habitable planet, we will look for ozone and oxygen the signature of ozone and oxygen molecule, and that will tell us whether life exists outside the solar system or not. If we detect it, that will tell that we are not alone. If we do not find it out, we have to continue our search. We just cannot say no, there is no life outside the solar system, but if we get biosignature, we can only know that we are not the only planet, we are not living in the only planet where life exists. So, in both way philosophically both the results are very important. Now, look out to our home, that is our planet Earth. So far we have only one planet that we know life originated here, life evolved here, life still survived and still exists here. We do not know if there is any other planets where life exists even in primitive form, let alone in intelligent form. There are several criteria. I have only talked to you about two conditions on the habitability, that is rocky planet and the temperature, but there are several geological and astronomical combination of favorable condition that enable life to survive on this planet, and this is the so far only planet known to us that has life on it. Now, if you look our home planet Earth from outside, it will look like a small blue dot with its moon orbiting it, and this image is taken by the spacecraft Juno, which is on its way to Jupiter at a distance of about 10 million kilometers from us. And this is the famous picture taken by Cassini. This picture is called the day Earth smile. So, here is the picture of that blue dot where we are living at the distance of 1.44 billion kilometer from us. During the early 70s, NASA sent a spacecraft called Voyager 2. Now, Voyager 2 has crossed the end of the solar system, and at a far distance about 6 billion kilometer from us, it turned back its camera and took a photograph of our planet, and which looks like a pale blue dot, just a dust, a point in the vast arena of cosmos. Now, this I have given an introduction of all that we know about exoplanet. For a non-technical study material, if you want to know much details about this talk, you can refer to the book written by me, is Worlds Beyond Our Own, the search for habitable planets. And if you want to go for further technical aspect of the exoplanet research about the details about the atmosphere and habitability and all those conditions, you may refer to the exoplanet handbook by Michael Perryman. This is the first edition. The second edition of this book has just now published. This is by Cambridge University Press. Can you find it out? So, these are two problems which you can apply for the solar system planet and find out the radial velocity of the sun imparted by Jupiter and Earth by using this formula. That is problem number 1. Problem number 2, if you have already heard about the transit of Venus, then use this formula to find out how much time Venus will take to pass the disk of the sun, that is what is the transit period of Venus across sun, and then you can apply it for other planets, exoplanets, etc. For other questions, you can refer to the books I have mentioned. Thank you.